Okay, so now it's time for the talk, and this talk is about private set intersection, and a lot of this work was done with Thomas Schneider and Michael Zoner from Darmstadt and Gil Seger from the Hebrew University. Part of this talk, some of you have heard part of this talk last year in Denmark, but towards the end I had new results that were not available last year. Okay, so this talk is different than the other ones you heard so far because it discusses protocols for specific problems. So these are not protocols for secure computation of generic programs of any program. They're just protocols for computing a specific, a secure computation of a specific problem, which I think is quite important. Okay, so one way for to solve that problem, to securely compute it, is to use any generic protocol like YAOS protocol or speeds. Okay, we turn to designing specific solutions if we think that the problem is important enough that we want to optimize its performance even further. So in many cases, the best performance we achieve is using generic protocols because people have invested a lot in improving them. But here we can achieve more. One reason is because the circuit representation of set intersection is not that efficient. Okay, so you can use generic programs, but they work on circuits, and the circuit representing the solution, the algorithm for solving this problem, is not very efficient. And the other is that if we look at a specific problem, we can have new insights and design a better protocol. Okay, so what's this problem? It's a private set intersection. So we have two parties, Alice and Bob, or client and server. Each of them has a set. Suppose that each of the sets has n items, x1 up to xn for the client, and y1 up to yn for the server. And at the end, the client should learn the intersection of the two sets and nothing else, and the server should learn nothing. So this is just one variant of the problem. We could think about other variants where, say, the two parties learn the output, or suppose they learn the size of the intersection but nothing about the inputs, or perhaps they only want to compute, say, 1 if the size of the intersection is greater than some threshold, or any other variant. Okay? But we'll focus on this specific variant for this talk. Now, this is actually a very natural problem, and it comes up in many settings. This is why we're interested in it. One setting is that of matching, so comparing human genomes to each other. Matching actually for dating applications. So people have their preferences, and the app, the app on my phone has my preferences for movies and other stuff, and potential partners have their preferences. And basically, to compute how well we match is computing the intersection, comparing the size of the intersection to the size of the domain, and so on. So computing matching, intersection, so it can be used to compute the intersection of suspect lists. So in cybersecurity applications, this actually comes out quite often. There are companies have lists of suspicious activity, say from specific IP addresses, and they want to compute, to say if the same activity appeared at different companies from the same address. However, they don't want to disclose to each other, the whole list of connections to their network, because this reveals some, private information of that company. So they would like to compute intersections while hiding anything else. Yeah. No. I was asked what proximity testing is, but I just leave it. There are dozens of applications. I'll describe the next one. Okay, so contact list discovery. So that's actually, these are names of 3 startups. Actually, pretty known one, TechSecure for messaging, Secret for posting anonymous messages about your friend, and Medium, it's a blogging company. And essentially, when you join these services, they want to see who of your contacts is already a member of the service, because then they can provide you with information which is more targeted, more towards you. Okay. However, if they care about privacy, and these specific applications do care about privacy, they don't want to learn the sets of your contacts. Just want to learn whom of your contacts are already members of the service. So they use some protocol for set intersection. Another very promising application, which I won't go into details because it will take me something like 5 minutes to describe how it works, is for measuring conversion rates of online advertising, mainly for showing how effective online advertising is. And this is a multi-billion-dollar business, and computing the effectiveness of ads is very important. And actually, Facebook reported that they're doing some sort of private set intersection, as well as these application companies, and I'll describe this in a minute. So in this talk, I'll survey the major results. I'll suggest some observations that we had and that improved the performance, and I'll present some new schemes. At the end, I'll compare the performance of some of the schemes on the same platform. This is something which we don't have in the general multi-party computation case, where people come with different numbers, but the numbers are on different platforms. So here we, or more Michael Zoner and Thomas Schneider, they took different algorithms, implemented all of them on the same platform, and compared the running time to actually compare all of them on fair environment. So how can we compute set intersection? So the first approach would be, let's just represent set intersection as a circuit, and then apply any protocol we have for secure computation to compute that circuit. However, the circuits turn out to be quite big, and I'll talk about this in a few minutes. Another thing that's easy to notice is that private set intersection is equivalent to oblivious transfer, meaning that if you have a protocol for private set intersection, you can compute oblivious transfer. This means that we cannot hope to implement private set intersection with overhead which is smaller than the best we know for oblivious transfer. Actually, we can hope to do that, but if we have a protocol for PSI, which is more efficient than the best protocols for OT, we can use that protocol to implement OT. Okay? So we cannot do better from OT unless we find something very surprising that will also give us a new OT protocol. And to show that, it's actually pretty simple. So Alice's input is a bit B, and suppose we just want to we have an OT protocol, OT problem we want to implement. Suppose it's an OT of bits. Alice wants, her input is B. She wants to learn item B. Bob has two inputs, X0 and X1. And Alice should learn XB. So Alice sets her set to include B0 and B1. And Bob uses his input set to be 0, X0, and 1, X1. And the intersection of these two sets is exactly B, XB. So Alice will learn XB. So this is an oblivious transfer of bits. Using oblivious transfer of bits, you can do oblivious transfer of strings. There are known reductions, and so on. So if we have a protocol for PSI, we can do oblivious transfer. OK, so how should we come up with a protocol for PSI? So if you ask someone for a protocol, that someone is not a cryptographer, then they usually come up with the following protocol. Okay, so here's a naive solution. So Alice and Bob agree on some cryptographic hash function age, which is one way of, say, a random oracle. And then Bob sends to Alice a hash of each of its elements. Now Alice computes a hash of each of her elements and just compares the two lists. So obviously, say if y1 is equal to xn, then age of y1 is equal to age of xn, and Alice will notice that the both items are the same. So instead of comparing the original items, they compare hashes of these items. And here, you can claim that this is secure because this hash function is one way, and therefore, when you get the hashes, you cannot go back and compute the original inputs. Okay? However, this solution is insecure. Does anyone wants to tell me when that solution is insecure or why? Okay. So, when I claimed it to be insecure, I said that it's hard to go from the output of the function to the input. However, if the inputs come from a domain which is not that large or doesn't have a lot of entropy, one can do a dictionary search, go over all items in the input domain, and compute the hash of these items. So suppose the inputs are IP addresses. And Alice receives the hash with the function age that she knows, like say SHA, of the IP addresses that accessed Bob. Now, what she can do compute hashes of all possible IP addresses. There aren't too many of these. Okay, 2 to the something. Okay, 32, right? So computing 4 billion hashes is very efficient. And now she has a table, and when she gets a hash from Bob, she compares it to the table, and she knows exactly what was Bob's input that caused that hash. And this is true wherever the inputs come from a domain which doesn't have enough entropy. It could be names of people, email addresses, credit card numbers, IP addresses. In all of these cases, this attack is very simple. However, this is the algorithm that is used by all the companies I mentioned. So the application companies, Facebook, this is what they're doing, and they claim to the FCC this is secure because this is a one-way function, you cannot go backwards. Okay? And our goal is to achieve a protocol which is provably secure and is not much worse than that protocol. And currently we're about, I would say, 5 times slower than that protocol with provable security. Okay? And this protocol is like, you cannot do better than that. It's like one hash function operation per item. Okay? And there was a question.
So what if a multi-cycle set to a whole dictionary?
Could you say that again?
If A would set to be the whole dictionary,
yeah.
Also learn the input of both.
Okay, so the question was, what happens if if one of the parties sets his or her input to be the entire dictionary, in which case, though it's Alice in this case, she learns all of Bob's inputs. So this question is relevant in all secure computation scenarios. So basically, what we do when we design secure computations, we tell our customers that design a protocol which makes sense in a setting where you have a trusted party. Okay, so design a protocol that where you want to compute set intersection where you have a trusted party, and all that we can do is get rid of the trusted party. So in this case, I guess your contact list cannot be too big, or there should be some other measure to make sure that the parties provide legitimate inputs to the protocol. The secure protocol cannot enforce the parties to provide legitimate inputs. All that it can enforce is to make sure that they don't learn more than in an ideal setting where they provide these inputs to a trusted party and receive the output. Okay. So this is something beyond our. So for instance, in the contact list example, my contact list cannot contain more than, say, 1,000 people or so. Okay, so some preliminaries. We'll only consider semi-honest or passive adversaries. There are PSI protocols secure against malicious adversaries. Kermit here is the author of some of these. They're quite efficient, but they're less efficient than what we do. As far as I know, none of them was implemented. And why they're less efficient? This is like one of the protocols. And you see these boxes, which are efficient zero-knowledge proofs of knowledge, I guess here and here. But okay, but whenever you have to do this, you have to do some exponentiations, and we don't want to do exponentiations. We want to do very efficient. We want to do hash functions. Okay, if you have to do exponentiations for every item, we're not going to be 5 times faster than the protocol that only computes hash functions. So we currently protocols secure against malicious adversaries are too inefficient for what you want to do. We're also going to work in the random oracle model. There are protocols that work in the standard model. I'll describe one of them shortly, but they're less efficient. They use exponentiations. We want to do better than exponentiations. Okay. So I'll start with a very old protocol, a very simple one. It's actually the easiest one to implement, and it can be provably secure. So here's the protocol. It's based on the decisional Diffie-Hellman assumption that most of you know. And basically it says that in a group where you have a generator G and random inputs A, B, and C, one cannot distinguish between G to the A, G to the B, and G to the power of AB from G to the A, G to the B, and G to the power of C. So you cannot distinguish G to the C from G to the power of AB. So here's the protocol. And surprisingly, it was presented even in a paper of Catherine Meadows from '86, although she doesn't say it there. Then it was presented again in a paragraph in a paper from '99, and then it was proved by that paper. And the proof is in the random oracle model, and the protocol goes like this. So Alice has a secret alpha, exponent alpha, and Bob has a secret exponent beta. And they have the list of elements. What Alice does, she computes a hash of each of her elements, raises it to the power of alpha, and sends to Bob. Bob takes each of his elements, computes a hash, of that element, raises to the power of beta, the value of that he knows, and sends to Alice. And afterwards, he takes each of the values received from Alice, raises also to the power of beta, and sends to Alice. Now, Alice received that list from Bob, but she also received the age of the Y's, Bob's inputs to the power of beta. So she raises these values to the power of alpha. Now she compares the two lists. So you see, suppose that x1 is equal to yn, so x1 to the power of alpha was sent to Bob. Let's see, he sent back x1 to the power of alpha beta to Alice. And Alice sent here, and Bob sent to Alice hyn to the power of beta. She raised it to the power of alpha, so she has age of yn to the power of beta alpha, and these two values are supposed to be the same. So if the same, so due to the commutativity of the exponentiation, if the same value appears in both lists, it's the same value is going to appear here and in the list sent from Bob, and Alice, when she computes the intersection, she'll notice that the same value is in the intersection. To prove security, you need to model age as a random oracle and use the age assumption. And the nice thing about this protocol is it's very easy to implement. So I guess most of you, even me, even if we haven't implemented anything for years, it's very easy to implement it. Okay, it's really straightforward to implement it. You can also implement exponentiations based on elliptic curve crypto, and then it's very efficient. Also, the communication, you just send elements in an elliptic curve. So you send the communication here is very small. It's actually ideal. In none of our protocols, we're not able to achieve as communication as small as in this protocol. Perhaps in the last one we're able to kind of improve by a little, but that's about it. So it's a very simple protocol to implement, and it's has very little communication. When you implement, you can notice that the exponentiations done by Alice here and Bob here can be done in parallel. The same here. So they can both utilize their CPUs to the max in parallel. So it's a very nice protocol. And if you're new to this, like if you want to start with something, this is the protocol to start. Okay. Like each of the other protocols I'll describe will take you weeks or months to implement, and this thing you can implement in a day. Okay, what else would we want? So one thing we would like is to get rid of the random oracle assumption, but we're not going to do that. And another thing is just to make it more efficient, not use exponentiations. Here we use like each party does 2 exponentiations per item. We'd like to do better than that. There's another variant based on public key crypto, which is based on blind RSA and not Diffie-Hellman. This is due to Dick Christopher and Tzudik. And the performance, I'll show it in a minute. The performance is similar to that of the Diffie-Hellman protocol. But because they're using RSA, one party has the secret key and one has the public key. Now the public key is usually short, like 3. So raising items to the power of 3 is very efficient, whereas the party that has the secret key has to work very hard. So whereas in the Diffie-Hellman protocol, both parties work have the same effort, here one party has very little work and the other works very hard. And also you cannot base this on elliptic curve crypto. And the protocol goes like this. Alice chooses random i's, and basically she blinds her inputs, actually doing blind RSA signatures. She sends each of her inputs to Bob, masked by R1 to the power of E. Bob knows the secret key D, so each of these values he raises to the power of D and sends back to Alice. And he also sends hashes of his y's to the power of D. Now when Alice receives these values, she gets essentially x1 to the power of D times R1. She can divide them by R1, compute a hash, and compare here. So if someone saw blind RSA encryption signatures before, this is essentially blind RSA signatures. If someone hasn't seen blind RSA signatures, then it's impossible to understand it from this slide. But perhaps at home you'll be able to do that. So these are public key based protocols. I just mentioned, and I'm going over many protocols, and then I'll go to the state of the art. If we don't want to have random oracle assumptions, they are protocol based on Oblivious Polynomial Evaluation. So to make the story short, what you do, you use an additively homomorphic encryption like Payet or El Gamal. Alice generates a polynomial whose roots are her items. So if her inputs are x1 up to xn, she generates a polynomial which is 0 if you evaluate it on x1, x2, up to xn. And you generate it by multiplying x minus x1 times x minus x2 and so on. She sends encryptions of the coefficients to Bob using homomorphic encryption scheme, additively homomorphic. Bob uses them to evaluate the polynomial. So for each of his items, he computes p of y. Y is his input, and multiplies by some random value and adds yi. So notice that if yi is equals to an input of Alice to some x, then p of yi is going to be 0. Okay. In that case, the first item here, the first element here is going to be 0. So he sends to Alice encryption of yi of his element, of the item which is in the intersection. If yi is not the root of p, then this is going to be some value which is not 0, p of yi. And since he multiplies it by some random value, then this whole encryption is of a random value. So you can prove this to be efficient, and it's a whole talk to discuss this protocol and its variants, and I won't do that, just mention the basic ideas. What I described here uses n-square exponentiations because you compute a polynomial for each item, and each polynomial is of degree n and requires n exponentiations. You can use hashing to reduce the number of exponentiations to n times log n, but we can do better. We don't want to do log n exponentiations per item. We don't even want to do one exponentiation per item. Okay. Then, people thought, well, let's use generic protocols for computing the intersection. So we have generic protocols for implementing, any circuit. So let's do a circuit computing set intersection, okay? And a naive circuit, well, what could it do? The circuit should compare each input of Alice to each input of Bob. So if each party has n inputs, the circuit should do n-square comparisons. And n squared is a lot. If n is 1,000,000, we don't want to do 10 to the power of 12 comparisons. Okay, so that's much too much. So this didn't seem like a good solution. Can we do better? So apparently we can. So a very nice circuit-based protocol of Wang, Evans, and Katz works like this. So it uses the sorting networks, which he already mentioned in the previous hour. And the idea is like this. The two parties should take their input sets, and then they should sort the union of the two sets. Okay? Now, after they sort the union of the two sets, if Alice and Bob had a value which appeared in both of their inputs, then in the sorted union, the two copies of that value are going to appear adjacent to each other. Okay? So after we sort the items, the union of the two sets, all we have to do is go over the circuit should go over the two n items in the sorted list and check if there are indices where item in index I is equal to the item in index I plus 1. This is a linear comparison. So the first step is to do the sort, and since the two parties each can sort its own input set independently, what they have to do is to merge two sorted lists. For this, you can use, again, a result from the 60s, Bitonic merging network, and it takes something like order of n times log n comparisons. This is like part of that network. The next part of the circuit, after we did this sorting, and we have adjacent copies of the same item being adjacent to each other, the circuit should look at adjacent items and check if they're the same. So this part of the circuit is linear. You just have to do one comparison for each index n. So that's efficient. There's two inequality checks. And then the last step is to shuffle the results, because we don't want to reveal to the person, to the party evaluating the circuit, that we found equality in the first pair that we compared. So it should shuffle them randomly. This takes another n log n mappings. And overall, if you count everything, if you have inputs of length L bits, the total length of the circuit, the total number of n gates, is L times 3n log n plus 4n, which is like a small order of n log n. And then a very nice observation that we made when we came to implement this is that if you look at this circuit, most of these n gates, what the implement is multiplexers. Okay? So suppose you're comparing two items, and you should output the smallest of the two items. This is what this. So This is what this circuit is doing, okay? So you first compare the two items, then you have an output bit which tells you which one of them is smaller. And then you need a multiplexer which checks which outputs either the first item or the smaller item based on that single bit, okay? So there's a single bit which is involved in many, many gates, okay? If the items are 32-bit long, there's a single bit which tells you which of the two copies to choose, and we're going to use this in a minute. So how can you use this? So the initial implementation was done using Yao. This is what AGK did. And he already had oblivious transfer extension. And we noted that GMW uses 2 oblivious transfers per gate, and Yao uses 4. So if we use oblivious transfer extension, we actually use less symmetric key operations per gate. So let's use OT extension. And then there was another, actually very nice observation. So if you look how GMW implements the protocol, okay? So recall what I described in the first day. For each gate, the parties in GMW do an oblivious transfer, where the input to oblivious transfer depends on the input of the parties to the gate. This is how it's done, but the details are not important. Now, we call that in the PSI circuits, 2/3 of the AND gates were for multiplexers. In a multiplexer, say, there's a single bit that decides on the outcome of 32 bits. If we're sorting 32 bits long values, a single bit decides on the outcome, where this string should go. So a single bit is involved in at least 32 AND gates. Okay? So instead of implementing each of these AND gates independently using independent oblivious transfer, we notice that actually the same value is used for the oblivious transfer in each of these 32 copies. So instead of doing 32 independent oblivious transfer, we just do one oblivious transfer, where the input that we transfer in the oblivious transfer is 32 times bits long. Okay? So essentially, we look at the multiplexer not as 32 independent gates, but as one gate where one input is small and the other input is large. And this reduces the number of AND gates dramatically and makes the performance much, much better. Okay? So the performance that we're able to achieve is much better, and also noted that to implement GMW, you don't need plain oblivious transfer. You can use random OT, which was discussed in the lectures on OT extension. It's more efficient than plain OT. So, okay. In spite of all of these improvements, we'll see at the end that circuit-based PSI perform less well than the other protocols we show. So they're essentially the less efficient PSI protocols that I'll describe. Still, I think that this is like circuit-based PSI protocols are very important. And the reason is that in a circuit-based protocol, you have a lot of flexibility in deciding which function to compute. Okay? So think about the protocol I described for the one based on Diffie-Hellman of the instantiations. If now I tell you that I don't want to compute the intersection, I want to compute only the size of the intersection. I want to output 1 if the size of the intersection is greater than 10 and 0 otherwise, or any other thing. Okay? Then if you go back to that protocol, essentially you need to call a cryptographer to analyze it and design a variant which computes the variant of the function you want to compute. However, if you have a circuit computing PSI, and now you want not to reveal the intersection, but just say output 1 if the intersection is greater than 10, you can call a student who just took the basic course in hardware design, and he'll modify the circuit for you. Okay? So essentially, the task of changing the functionality now is not a task for cryptographers; it's a task for programmers, or very simple programmers. Okay? So it's very important to have efficient protocols that are based on circuits, because it's much easier to reprogram a circuit than to design a new cryptographic protocol. Okay? And towards the end of the talk, I'll describe a new and improved version of a protocol based on circuits. Okay. So when we came to improve performance, what we noted that the most efficient tool we have is OT extension. Okay? So everything else is less efficient than OT extension. So let's just use OT extension to the max and do whatever we can. Try to see what we can do with it. So the protocols are based on OT extension and hashing, and they achieve pretty good performance. Okay. So this is a new set of protocols. If someone lost me, they could come back. So the simplest case of set intersection is where they just want to compare one item. So Alice has one item and Bob has one item. This is the simplest case because it's just one item, okay? So suppose the inputs are s bits long and they should output, the protocol should output if the two inputs are the same or not. So here's a simple protocol based on OT. Suppose that Alice's input is 0, 0, 1 and Bob's input is 0, 1, 1. And they use random OTs. So in each random OT, they use 3 random OTs because 3 is the length of the inputs. In each random OT, Bob learns the 2 strings, and Alice learns 1 string, and she chooses to learn the string that corresponds to her input bit. So since her input is 0, 0, 1, she learns the first string in the 2 first pairs and the last string in the last pair, because this corresponds to 0, 0, 1. Then the next step, Bob he learned all the pairs, but he XORs the values corresponding to his input. So his input is 0, 1, 1, so he XORs the values corresponding to these red inputs and send the XOR to Alice. And Alice computes the XOR her values and compares, okay? So we call that these values are equal. So if Alice's input was different, well, if Alice's input was equal to Bob's, they both compute the same XOR, the XOR of the same strings. The 2 strings will be equal. If her input is different than Bob's, then the string will be different unless they happen to be equal by luck. And if the strings are random and of length lambda, then the probability of positive for equality is 2 to the minus lambda. And we should set lambda accordingly. So why is it correct? I just described to you. Why is it secure? We can simulate security because the only message that Alice receives here is either a value which is equal to her input to what she computed if the 2 inputs are the same, or a random value otherwise. And it's pretty efficient. So for inputs of length s, we do s random OTs, and then Bob sends lambda strings to Alice. And we can implement the OTs very efficiently using the OT extension. Now the next step is what we call private set inclusion. And here Alice has a single input x, and Bob has n inputs. So we want to compare n to n. We started with comparing 1 to 1. Now we're doing 1 to n. Okay? So, and we want to know if x is in that set. So what we can do n independent tests to check if x is equal to y1, equal to y2, and so on. Each of these tests will do an oblivious transfer for each row in the matrix. But notice that Bob's choices, or Alice's choices, in each of these oblivious transfers will be the same for all of the strings. Because in this matrix, you should choose something that corresponds to her string. And there are many matrices, but in each row, in each matrix, you should choose the same input. So instead of implementing the n oblivious transfers in parallel for each row, we can just do one oblivious transfer, where Alice just learns strings that are n times larger, okay? Because you choose the same in each of these, OTs, and instead of learning strings, you can just learn a seed and generate the string from that OT, and then repeat the protocol. So it's very easy to fill the details here. And then the last item we want to achieve is to compare n strings to n strings. So now Alice has n string x1 up to xn. So we just repeat the previous protocol n times. Check if x1 is in y1 up to yn, x2 is there, and so on. And the communication, if we compute it, is n squared times lambda, and n might be 1,000,000, so that doesn't look nice. Okay, it's a lot of communication. Okay, but we can reduce communication using hashing. So let's reduce communication. Now, the basic idea is, okay, instead of comparing each of Alice's item to each of Bob's item, let them first use a public non-random hash function to map the n respective items to n bins. So each of them uses the same hash function age, and each of them maps his or her inputs to n bins using that age. So item I essentially goes to bin age of I. Now, obviously, if Alice and Bob have the same input x, then both of them are going to map that input to the same bin. Okay? So now I don't have to compare each of Alice's inputs to each of Bob's inputs. I only have to compare the inputs that Alice mapped to bin number j to the inputs that Bob mapped to bin number j. And so instead of doing n square comparisons, I have to do sigma of the number of items mapped to that bin squared, which should be much smaller. Okay? So we expect if you map n items to n bins, I expect each bin to have just a constant number of items. And I compare a constant number of items that Alice mapped to the bin to the constant number of items that Bob mapped to the bin using a constant number of comparisons. So I'm only going to send a constant number of strings, and the communication per bin is going to be some O of lambda, the length of the string I'm sending to check if they compute the same value. So overall, the communication is only n times lambda. But there's a problem here. The problem is that if we map n items to n bins, we expect to obtain just one item in every bin, but that's only the average. It's not always the case. Some bins are going to be empty, and some bins are going to be more populated. Okay? Now, Alice cannot tell Bob, like, look, Bob, in this bin I didn't map any item to this bin, but in this second bin I have 3 items mapped to that bin by this hash function age. And that's because Bob knows the hash function. If he knows that Alice didn't map, say, any item to bin number 1, and he knows that age of this IP address is equal to 1, he knows that this IP address didn't appear in Alice's input. Okay? So Alice cannot tell to Bob which bins are more occupied or less occupied. So we must hide how many items we map to each bin. And the only way we know to do that is to pad each bins with dummy items. Okay? So we should compute what is going to be the size of the most populated bin. And if we map n items to n bins, then with very high probability, the most populated bin is going to have log n items. So we're going to pad each bin to have at most log n items, to have exactly n items. Okay? So in the most populated bin, we don't have to add any more items. In other bins, we have to add more items until we have exactly the same number of log n items in every bin. And this increases the communication by a factor of log n to n sigma log n, and we don't like that. Log n could be 20, so that's bad. Yeah?
Why isn't it log squared then? Because you can do many equation quality checks.
Why is the log?
Why isn't it log? If you have to compare 2 bins of size log n.
Yeah. Because the communication is not quadratic in the number of items mapped to the bin. It's only linear because you don't have to send value for each of the OTs. You do just send the seed, and from that you generate all the values. Okay, but you can do better hashing. Well, for instance, if you map n items to n over log n bins, the expected size of a bin is order of log n, obviously, if you map n items to this number of bins. And also the maximum size of a bin is with high probability the same, also order of log n. So this is ideal. This high probability here is not that high, but suppose that it's high enough. And then we can attempt to see what's happening. So this is, we investigated different hashing schemes. So if we do no hashing, this is the communication. If we check sets of 256,000 elements, then the communication is like 327 megabytes. If we use simple hashing like the one I described, the communication is 475 megabytes. And balanced hashing and cuckoo hashing are 2 fancier methods of hashing which achieve better performance. And you see that using cuckoo hashing, you can save quite a bit. Okay? So you can reduce, by using hashing, you can reduce the amount of communication by over 3 orders of magnitude here. Okay? But you have to take care to do the right kind of hashing. Then that was the situation last year. And then we had another observation. So the protocol essentially performs an oblivious transfer for each bit of the inputs. Okay? So if I have, say, the input is an IP address which is 32 bits long, I should do 32 oblivious transfers. Perhaps so, if I can reduce the input length, I'll do less oblivious transfers, and then the communication will reduce linearly. If I use half as many input bits as input, the communication will be reduced. And here's the first idea, which unfortunately doesn't work. And it goes like this. So if I map n items to n over log n bins, then each bin has about log n items. Now, if you recall the birthday paradox, if I have log n items, if I map the identities at random to a domain of size log square n, or slightly more than log square n, then I won't get any collisions. So why not just hash the IP addresses to smaller representations of size log, of items in the domain of size log n square, log square n, and then we won't have any collisions because the domain is the squares of the number of items we have in that bin, and the representation is much smaller. Okay, and it seems like very promising because if n is 2 to the 20, we want to compute the intersection of 1,000,000 items. Then log n is 2.6. So the presentation, if you can do a presentation of that size exactly, that's amazing. But even if you have like a factor of 4 in front of that, it's like a presentation of size 10 instead of 32. So we improve the performance by a factor of 3. That's amazing. Unfortunately, it doesn't work. So if you look more carefully at the proof of the birthday paradox, you see that to make sure that collisions don't that the probability of collision is only 2 to the minus s, the length of the representation after making it shorter is s plus log n. So if you look at it asymptotically, the length of representation is only log n. That's great. Okay. However, what would be the probability that that with which we're able, we're willing to tolerate collisions? Okay. So if we have 1,000,000 items, I would say the probability of a collision in any single item could be something like 2 to the minus 40 or so. In this case, s is 40. So if we use this hashing tweak, the length of the representation will be at least 40 plus 2.6 or log n. So we lose a lot by using this hashing. Asymptotically for huge n's, it would it makes sense, but it doesn't make sense here. So to reduce the length of the representation, we use a very neat idea of permutation-based hashing. Actually, you should listen now. It's really a cool idea. So the source is a paper by Arbatman, Naor, and Segev. And the idea is to hash items to bins, use short representation while ensuring that we don't get any collisions. We won't get any collisions with probability 1. I mean, it's not a probabilistic construction, it's a deterministic one, and we won't get any collisions. Okay? And it goes like this. So assume we have 2 to the b bins, like 1,000,000 bins, and the input length is x, which is much larger than b. So let's go to the second slide. So assume we have 2 to the 20 bins, and the inputs are 32 bits long. So I'll go back. So we look at each input x as being composed of the left part and the right part. And the left part is going to be 20 bits long, exactly, log of the side number of the bins. Okay? So essentially, the left part is an index which decides on an identity of a bin. Okay? So I'll go back. And then f should be some random function whose range is also the domain of bins, from 1 to 1,000,000, from 1 to 2 to the power of b. And then item x is mapped to the bin xl, the left part of x, XOR to f of xr, and we store in that bin the value of xr. So in our example, okay, xl is 20 bits long. We have a function f, which is random, and its domain is of size 20 bits, so 2 to the 20. X is mapped to a domain, to bin xl, the 20 left bits of x, XORed with f of xr. F of xr is also 20 bits, so this is a value, a 20-bit value. And we store only the 12 remaining bits of x, only xr. So we only store the 12 bits. So this construction reminds us of Feistel constructions for symmetric, for DES, okay? And we map x to that bin, and we store that value. And the property we want to achieve is that even though we stored very short values in the bins, we still provably would not get any collisions. So what we want to prove is that if x and x prime are mapped to the same bin, and x is equal to and what we store there is the same value, then x is equal to x prime. So let's see why this happens. So suppose x and x prime are mapped to the same bin, and we stored at the same value. So xr is the 12 write bits of x are equal to the 12th write bit of x prime, because we have the same value in the bin. But if that is the case, also the bin to which we saw them must be the same, because we know that the bin that x was mapped to is equal to the bin to which x prime was mapped. We know that xr is equal to xr prime, so f of xr is equal to f of x prime r, therefore xl is equal to xl prime. So what we get here is that if two items were mapped to the same bin, and if the 12 bits that we store in that bin are the same for these two items, then the original much longer items were equal, okay? Because both the decision were to store the item and what we store in the bin kind of depend in a very efficient way on the original representation of the items. And this is, like, I must say, it's a very nice idea. It's really nice. Only two. So in this example, so if I have 2 to the 20 bins and the inputs are 32 bits long, I use the left 20 bits to define the bin. So the bin is defined by the left 20 bit and the function f of the right 12 bits. And what I store in the bin is only the remaining 12 bits. So I only store in the bin 12 bits and not 32 bits.
So use the identity of the bin to...
So what the theorem says that if two items are mapped to the same bin and they have the same representation, then the original two items were the same. So we gain a lot by that, yeah?
Sorry, is this like a variant of perfect hashing that you have, or is it perfect hashing under a cryptographic assumption? Like perfect hashing gives the same thing, right?
Well, the perfect hashing, okay, perfect hashing, you mean that each bin has exactly one item.
Yeah.
But the constructions of perfect hashing, you define the hash, as far as I know, okay? The hash function you use is not oblivious to the items you have. You decide which hash function to use.
Probably.
Yeah, so it cannot happen. No, even so you start first you map to bins, and then in the bins where you mapped more than two items, you do a second step. So in perfect hashing, you cannot have that Alice and Bob use the same perfect hashing because they have different sets of items. And here it's very nice. They use the same algorithm, and you can represent much smaller values. And yeah. Yeah.
Is it clear that only one value will be stored in each bin, or can there be?
Okay, no, there could be more than one value in each bin.
And don't you have to hide that, or?
So again, as in the previous construction, there might be more than one value mapped into each bin. Okay, so we still have to pad as in the previous construction, but what we gain is that what we store in each bin is only 12 bits instead of 32. So now for each item, we have to do 12 oblivious transfers instead of 32. So this is like a factor of 3, almost a factor of 3 improvement. Okay, and a very nice trick to show. Yeah. Okay, so that's very nice, and that's the first, I think it's the first time this idea was used in a cryptographic setting. And we had other improvements, which I won't show, and trying to make this even more efficient. The interesting thing here is that once you start achieving this performance, everything starts to count. Just moving data and computing source and things like that count almost as much as cryptographic operations. So you have to be very efficient when you do these things as well. Yeah?
So in the previous constructions, the number of bins depended on the number of items I had. Now it depends on the total domain of bins.
Okay, so I'll repeat the question. So the question was that before I said that the number of bins depends on the number of items I had, like n or n over log n bins. And now somehow I connect between the number of bins and the representation. So again, so what I'm saying here, decide, what I try to say is that you decide on the number of bins based on the number of items you have and the hashing function that you used, okay? But after you decided on the number of bins, don't just use the hashing function that I described here, okay? Well, this hash function, okay? And then you can store much shorter values in each bin. So do all the calculations as before, but this lets you, by using this hash function, which if f is random, it's as random as any other hash function, you're able to store much shorter items in every bin. That's really a nice trick that can be probably taken to other applications. Okay, and you save a lot. Okay, and another thing you can do here, so recall I said that generic computation is very efficient. No, it's not very efficient, but it's very useful. So we try to use permutation-based hashing to improve generic computation. And the idea is as follows. So, okay, I should have given some drawings here, but I'll just describe it. So the parties map their items to bins using a hashing scheme. And then they use permutation-based hashing to make the bins, to make the representation as small as possible. And then in each bin, just do the stupid circuit, just compares all the items mapped by Bob to that bin to all the items mapped by Alice to that bin. And this shouldn't cost much because we're going to have very few items in each bin. So that's the simplest thing to do. And why is it good? So the previous circuits I showed, short, compare, shuffle, they have constants and they work on all the items at once. And all the items at once, then you cannot use the permutation-based hashing trick to make the lengths shorter. And here, no, we have much shorter items. And also the string is very simple. We just do the circuit is very simple. We just do comparisons and then compute output bits. So if we look at what we get here, so our new circuits, okay, the total number of gates is, okay, n sigma log n, where sigma is the new length of the representation, this 12 bits, whereas short compare shuffle had n sigma prime log n, where, okay, sigma prime was the previous length, 32. Now, also know that we have exactly n sigma log n, whereas they have order was something like 3 or so, okay? So we achieve, I guess, at least a factor of 10 here or so. Something else which is even more important, you notice that our circuits just compare items and compute a bit which is 1 if they are the same and 0 otherwise. So the depth of the circuit is log n. No, it's log sigma, where sigma is the size of the representation, sigma is 12. So the circuits are very shallow. In the sorting networks, where this sorting circuits were not that shallow at all, and if we use GMW-based protocols, we do a communication round for each level of the circuit. So we can achieve much better performance if the communication channel is not very, very fast. And indeed, our measurements show that. So the depth affects the communication rounds. And another thing to notice is that the circuit we use is very regular. It just compares strings which are sigma bits, log sigma bits long. Okay, sigma bits long. Okay, this means that we can generate the circuit much more efficiently. We need less memory to represent it. It's very easy to generate it on the fly. Okay, this also adds to the performance. So I'll show some measurements. So before us, there was no previous comparison of all protocols. I'll show some measurements with 2 desktops and a LAN and in a cloud setting. Inputs are 32 bits long. Statistical security parameter, the probability of something bad happening is 2 to the minus 40. And the symmetric security parameter for encryption is 128 bits. These are the results for 64,000 items. We don't say a lot here, so I'll move to the next slide. Okay, so the first item which is highlighted, the red one, is the insecure protocol, the one that Facebook and the other application uses. It just applies a single hash function. Okay, the last one is the most efficient protocol that we have. Okay, and here we're slower by a factor of about 9 in a local setting and maybe 6 in a cloud setting. If we look at more items, say 2 to the 20 items, then the ratio is about 6.3 against us. And for 16 million items, we only something like 3.4 times slower than them. Now, in these measurements, we used SHA for the hash function, not AES and I, because it's a nicer cryptographic assumption than to generate a hash function from AES. If we use AES, then we can improve by about 30% or so, okay? So we're slow by about a factor of, so for 1 million items, if I reduce the 30%, it's maybe a factor of 4 or 5 compared to the naive insecure protocol that they're using. And perhaps it's possible to claim that their protocol was probably optimized to the most, because there's not a lot of wrong things that you can do implementing a protocol which just computes hashes of inputs. So it's not that we didn't even optimize their protocol, because it's kind of a fair comparison. Okay. If I look at the generic protocols for computation, then the first one is the sorting circuit. After we applied to it the optimization of using just 1 OT instead of 32, because we just use multiplexer there. And the second one is the permutation-based hash protocol. And you see that the new protocol is about 4 or 5 times faster, but still these protocols are slower than than the OT-based protocols. They're slower by quite a bit. Now, if you look at the Diffie-Hellman protocol based on elliptic curve, well, it's almost the slowest one, but it's definitely the fastest one to implement. So I would say if you want to implement Diffie-Hellman, you can do it tomorrow. If you want to implement any of the other protocols, you have at least 2 papers to read and a few weeks of development time. So if you need this, you should start with the Diffie-Hellman solution. So regarding communication, naive insecure hashing just send hash values. The Diffie-Hellman, you send elements in elliptic curve, which is very short. The circuits, we have to send a lot of gates, so they're about 100 times, at least 100 times, or more than that, need at least 100 times more communication than the other protocols. But our permutation-based hash and OT protocol is not much worse than Diffie-Hellman protocol. So it's almost like only 50% more communication. And if you go back, in terms of runtime, it's like 100 times better. Okay, so that's nice. So to sum up, so today we can apply set intersection to very large input sets very efficiently. Almost as efficiently as the insecure protocol that companies are using today. And in different settings, you might need different protocols, depending if you want to optimize the runtime or the communication or the development time or the generality of the protocol on what you want to, if you want to be able to change what you're computing with it. And overall, I might say this work in this area provides a nice combination of both crypto and ideas from hashing, and systems ideas to know how to implement this efficiently. So it's a very nice research area. That's it.